Hello. All right, guys, the thing I want you to get is with these polar areas, you're adding sectors. So you get this weird situation where with rectangular coordinates, if you integrated x squared dx from 5 to 5, you'd get 0, right? And you don't even have to go through the trouble of taking an antiderivative. But that doesn't happen with polar graphs. Because with polar graphs, you start and end at the same point, but you get an area. Because what we're adding aren't rectangles, we're adding pizza slices. So when I integrate from 0 degrees all the way to 90 degrees, I'm actually adding up all of these pizza slices. Then I get back to 90 degrees. You go, wait, I'm starting and stopping at the same point. But you go, no, it doesn't work that way. You're adding all of these pizza slices together. And sure, you get back at the same point you started with, but you've got all that area. Okay, so this area is going to be the integral from 0, but I don't put 90 degrees, no siree, because we have to be in radians mode. So this is 0 to pi over 2, 1/2 4 sine of 2 theta, quantity squared d theta, and this ends up being 2 pi, 6.28 approximately. Are there any other questions on this before we start doing more? Okay, then hey, let's do more. I'm going to give you like 4 more to do. Here it comes. Shared number 2. That's equal. We're in trouble. Oh, that's it. Shared area of r equals 3, 1 plus sine theta, and r equals 3, 1 minus sine theta. Okay? First of all, you guys are going to graph this, of course. Tell me, what should your x min and x max and y min and y max be? From what to what?
From 6 to -6.
You guys okay with that? -6 to 6. So please set your calculator up, -6 to 6, and then graph that sucker. Yeah. Yeah, sure. If you got. What's that?
Wait, what?
Okay. Yeah, if you gotta go, you gotta go. Yeah, parents trump everything. You know what I mean?
And for the second one?
Well, I mean,
Did you just get
well,
0?
I'll use the max value and then just take the negative of that. That's usually how it goes. I mean,
Okay. Did everyone get something that looks like this?
not yet.
And I hope everyone gets that the shared area is this area right here.
Bless you.
So what you gonna do now? Mm-hmm.
Take the first equation and subtract it from the bottom.
No, you don't do that. I'm so sorry. That works in rectangle land. In rectangle land, where if I have this guy on top and this guy on the bottom, and we're adding rectangles, then the height of each rectangle is the difference between the functions. But I don't get to do that here. Here I'm adding pizza slices. And I can't say that a pizza slice is one radius minus the other radius. It doesn't work that way. Yes?
For the top graph, you can do the integral from 180 to 360, and it'll get you the bottom half of that. And then you can do the opposite for the bottom graph and add them.
Okay, hey, let's do that. Let's go ahead and do that, and let's write our little pizza slices and see what that gets us. Okay, step 1, trace. Trace. notice I start there. I'm going from 0. Tell me, am I interested in any of these pizza slices here?
No.
No way, I only want the guy's eyes. You know, if you can think of this as his eyes and then his nose, then his mouth, you know? I only care about the guy's eyes. So I'm not going for his big forehead.
It looks like a jug.
Okay. So I keep going until finally I get here. I get there at 180 degrees. Okay? And this is where Carly is starting. 180 degrees. All right? And now I'm going to go down till I get to the origin. And that happens at 270 degrees. So I'm at the origin of 270 degrees. This is 180 degrees. That's 270. And this is the graph. Okay? I want you to notice that's this graph here. My calculator tells me which graph I'm on. And I'm on that graph right now. Believe it or not, this is all I need. I don't have to be as complicated as Carly says. Because tell me, if I integrate from 180 to 270 of that graph, if I add up all of these pizza slices from 180 all the way to 270, what have I just found?
Half of the eye.
Good, half of one eye. Or if they're interested in the total area, what fraction of the total area?
1/4.
1/4. That's all you'd have to do. So your area, the area is going to be 4 times that integral from 180 to 270. But you'll notice I have to be in radians mode from 180 to 270 of 1/2. And I'm looking at the top, I'm looking at this graph, the top graph, 3 times 1 plus sine theta. So 3 times 1 plus sine theta squared. Okay, theta. And that's all you have to do. You guys okay with that? So you get paid off for being clever, but you're going to have to think in terms of pizza slices. You can't be thinking in terms of rectangles. Now your way, Carly, may have worked. I'm not sure, but I'm going to go with my way. So here we go. Second quit. Make sure you're in radians mode. So I got 4 times the integral of, do you mind if I just make it 2 times the integral and then I get rid of that 1/2?
Yeah.
2 times the integral of, I'm just going to go 9, and then 1 plus sine theta squared, comma theta, comma pi, comma 3 pi over 2. Again, everyone's calculator is different, but my ancient TI-83, I did that. You'll notice there's things you can do to make your life a little easier, like me combining the 4 and the 2, and me just squaring the 3 to make it 9, so the only thing I really had to square was the 1 plus sine theta. There's things you can do to reduce your chances of error.
Why do we do it in radians? For the
Because
integral?
the integral of the sine of theta is equal to the negative cosine theta only in radians. The integral of the sine of theta equals like 1 over pi times the negative cosine theta if I'm in degrees. Or maybe it was pi over 180. I forget, some crazy thing, but we don't want to have to deal with that. So yeah, those derivatives and integrals are only good in radians, so that's why we have to use radians.
Oh, okay.
So 6.4. Anyone get 6.4115? Oh yay! I must have got it right because Amber and Daniel got the answer. Woo.
Are you happy, Daniel?
Yes.
So I guess I'm going to round to the nearest thousandth because that's what they want on the AP exam. 6.412. Any questions or problems on this process? Because I'm going to give you another problem.
Hold on. Yes.
Okay. Hey, here we go.
What are the units on that, or the unit list?
It would be whatever the area is, square meters, square inches, square whatever, because it's area. Okay, hey, here comes example number 3. Okay. Get area shared by r equals 3 and r equals 6 cosine 3 theta. Please graph this. I'm going to do this problem, and then I'm going to give you another one just like it that you guys get to do. Abigail, are you able to see that well enough from where you're standing?
Yes.
Okay. Then I can just leave it here because it's a convenient place for me to put this. R equals 3 and R equals 6 cosine 3 theta. What's my window? Oh, my window's good. Make sure you're in degrees mode. Does everyone have that graph? Are you guys good with that graph?
Oh,
Did you know this is the last topic of chapter 10?
So we're gonna have a test too?
Yeah, we're gonna have a test real soon. Mr. Morrison was hoping for this Tuesday, but I won't be able to give it this Tuesday. Okay. Are you okay that the area shared, you gotta really have a sense of what it is. The area shared by both graphs is gonna be this guy, and this guy. Is that okay with you guys? That those are my shared areas?
yes.
So let's talk strategy. What am I gonna do? And Andrew, I appreciate you, but let me get someone else. What am I gonna do? What would you recommend I do?
Find the area of those 3 parts.
No way. Someone tell me, what should I do? How am I gonna get
Those
this?
down at the top.
I love you dearly, Daniel. Good try, but no, that's not your strategy. What's my strategy gonna be? He said, find the area of the 3 parts. No, that's not your strategy. Yes, Abigail?
Did you find the area of like a little loop from the one point to the other point?
You mean this entire petal?
No.
Oh.
From that part to there, and then multiply it by 6. And then you
Oh, okay. So Abigail is saying, hey, why not just find this area and multiply by 6? Will that work?
Yes.
Sure. Was anyone thinking, why not just find, let's say, this area and multiply by 3? Was anyone thinking that? Yeah, oh, so you were thinking that, Daniel. Okay, then yeah, either of those are good strategies. The thing you don't want to do is write 3 separate integrals and add them up. Don't do that. Take advantage of the symmetry of the situation. That's all I'm getting at. So now, here, let's take, let's do trace. Let me see where I am. Oh no, I just messed up my drawing. Oh, wait. That's so weird because I have to go backwards from what I'm looking at. Okay, great. Okay, so plus trace, alrighty. And do you see I'm there? And then I'm on the circle there. By the way, on my calculator, if I press the up arrow, I switch from my circle to my other graph. So, you know, So like if I go to 0 degrees, okay, I'm on the petal here, or if I press the up arrow, I'm on the circle, okay? All right. I'm gonna do, oh shoot, I'm not gonna try to make it fit that. I'm just gonna solve my problem by erasing it. All right. By the way, I'm doing this problem because I'm gonna give you guys one to do, okay? So I want you to see that 0, I'm there on the petal, and then I'm there. And do you see that's r equal 3, theta equals 20? If I press the up arrow, I'm at r equal 3, theta equal 20. Because you're going to have to find that intersection point. You need to know what this intersection point is. And the way you find it is you just go on it and then press the up arrow and see if you keep getting just the same coordinate, r equal 3, theta equal 20. Whether I'm looking at the circle graph or the 3-leaf clover or whatever, I'm at the same point. So this is 20 degrees. Okay? And so if I integrate the circle from 0 to 20 degrees, I get this sector of the circle. But here's the problem. Let me blow this up. Okay? Here's what I'm getting. Okay? Okay? Right here is 20 degrees. And when I add the sectors for my circle, I'm getting these sectors all the way to 20. But do you see, I've left behind this sliver. Okay? All doing the circle, integrating the circle from 0 to 20 only gets me this sector from 0 to 20. It doesn't get me this blue sliver. This blue sliver is bordered by the 3-leaf clover. So if I get onto this 3-leaf clover, do you see how I'm at 20, and then as I come down, I'm at 25, 30. 30 gets me to the origin. I'm going to have to add up my sectors on the 3-leaf clover from 20 to 30 till I get to there, 30 degrees. You see? So this area ends up being the circle, the integral from 0 to 20 degrees. And by the way, 20 degrees, what is that, pi over 180? So pi over 9 is 20 degrees. So 0 to pi over 9 of 1/2 times 3 squared d theta. That gets me the circle. And then I'm going to have to integrate from pi over 9 to pi over 6 of 1/2 6 cosine 3 theta, quantity squared d theta. Do you see that? To get this little half area here, I'm going to have to integrate the circle from 0 to pi over 9, and then the 3-leaf clover from pi over 9 to pi over 6. And then, actually, once I get this area, what am I going to have to multiply it by to get the total area?
6.
Yeah, 6. So I'm doing it Abigail's way. Multiply by 6. Is that okay with you guys? And then at this point, I hope you don't mind, I'm not going to punch this in my calculator because I need you guys to do a problem on your own now.
How did you know that the circle was at 20 degrees right there? Oh, because it's...
Because I use the trace button. There's no, I mean, there's other ways to know. I could use algebra, but I sure don't want to use algebra. I use the trace button. Yeah. Okay, you guys, so for the next 13 minutes, this is the last problem of tonight's, well, no, actually, it's the second to last problem, but it'll probably be the last problem of today's lecture. Okay. Get area shared by r equals radical 3 and r equals 2 sine of 2 theta. Good luck. If you can get that shared area, you win. There's one more problem I could show you, but this is the big one, the humdinger. See if anyone's good. Good. But you know what, Jawad, can I just interrupt you for a second?
Yeah.
Are you okay that the symmetry of the situation means you can just double your second integral?
Okay.
Yeah, I just want to, I mean, I'm supposed to let you struggle on your own, but you know, I'd rather just tell you. You mean the intersection point?
Yeah.
Do the trace back, so where you think the flashy dot is actually on there? Okay, good. You see it 60 degrees? Now press up arrow, and do you notice you get the same R whether you're on the circle or the 4 before? So that tells you, hey, that's the intersection point. Struggling with that stupid calculus. I hate the X
Really? I love
Can I see what you're doing? So you went from 30 to 60, yay, and then you went from 60 to pi over 2. Good, good, okay, good, great. And now here's one thing, you need 2 of those slivers, right? You have one sliver from 60 to 90, but you've also got another sliver from 0 to 30. So just double that integral, and then everything else is beautiful. So, this one has me. Yay, oh, you're so smart. John would say you're so smart. So where's yours? Okay, good. So you went from there to there, good. And then you added that. And the other thing, but you know, by symmetry, you could have just doubled that integral, and that way you don't have to plug in for the integrals. But yeah, you're perfect. Okay, good. Wait, what the heck? What pi over 12? How are you getting pi over 12? Something is wrong with your calculator. The intersection is 50. Oh, wait. Let me see what you plugged in. That's a different function. Yeah, 2 sine 2 theta. How fun. So, yeah, you were correct. So, anyway, Kimberly, you were doing it right. Wrong problem, but you were doing it right. Hey, so far, so good.
So it's 2 times the
Let's see what you got here.
It's a.
Okay, cool. Now, you're not going to multiply by 8 this time because you're getting the entire area.
Oh, so it's just 4.
Yeah. Okay, good. Great. Okay, so that's getting you the circle. Okay, now you want to get that sliver. And that sliver is from pi over 3 to pi over 2.
Oh,
Not pi over 4. It's 60 to 90.
oh.
And one more thing, there's 2 of those slivers. So you're going to have to, double that integral. See what you got? Yeah, see, Alessandro, you don't have to do that guy plus that guy. Why not just get that guy and then double it? Because of symmetry. I'm going to see if I can get, oops, I messed up the camera. Sorry. Yes. Yes, yes. And then what you can do is just double that integral, because you've got 2, here, just a second. Because you've got 2 slivers, right? You've got this sliver and you've got this sliver, so you can double that integral. By now, most of you seem to be getting, like, going from 30 to 60 to get the circle. And then you're either going from 0 to 30 or from 60 to 90 to get the sliver. I just want to remind you, there's 2 of these slivers. So you can go from 0 to 30 and then double it, or you can go from 60 to pi over 2 and double it. Either is fine.
Okay, that's weird. Oh my god. So you see, so from 0 to 30 degrees of the outside circle, if you take that and multiply it by 4, you get the same thing as if you found the 30 to 60 of the normal circle, of like the circle inside the petal. Really? Yeah, look.
So here I did the right down. Pi over 3, pi over 6, pi over 3. Just 30 to 60. That's from 0 to 6. And I think the same thing as
You know what, I'm going to use my other thing.
Oh my god. It's a reference. No,
That would stop it, yeah.
it's just the integral, right? They're the same in balance. Pi over 3.
Oh, but mine. Did anyone get 5.598? Oh, yay. Okay, good. Good. Before I go on, obviously getting the integral correct, if this were a 5-point problem, getting this correct is 4 of the 5 points and getting that is the 5th point. So is there any question or issue on the integral itself? You guys good on that? Getting the circle, getting the slivers,
Wait, why did you get the slivers?
Well, because if I just integrate the circle from 30 to 60 degrees,
Yeah.
all I'm starting with a straight line from the origin to 30 degrees, and I'm leaving out all of this part that's happening from 0 to 30 along the four-leaf clover. So yeah, I can't just get the circle area, I gotta get these two guys too.
Okay.
Yeah, because I'm just adding up, like I always say, I'm adding up sectors, but sectors are straight lines, you know?
Oh no, I was
Once
talking
get to
about
60, I'm
the
done.
blue part because I was confused. I thought I was confused. Never mind.
Well, guys, any other questions or issues on this problem before I just show you one last problem that I'm not even going to do? I just want to show you the how to deal with it. Here's our last example. This was example number 5. We're not going to get to it, but I want to at least graph it. R equals 1 plus 2 sine theta. Get area outside inner loop. Get the area outside the inner loop. Let me show you what I'm talking about. And hopefully the bell doesn't ring, but if it does, then we'll talk about it tomorrow. 1 plus 2 sine theta. Okay? I'm going to have to go from -3 to +3. Okay? Here comes the graph. Okay? Do you see how I've got an inner loop and an outer loop? The only thing I want to remind you of is to avoid redundancy, because when I press trace, I start there, and I'm getting all of these pizza slices, all these sectors, but I want you to notice that the areas I'm getting are including the inner loop. So right now, all of this is getting me the inner loop. So let's say I integrated from 90 degrees to 0 here, which I assume is 270, I don't know, 180? Here, just a second. No, 210. So if I integrate from 90 degrees all the way to 210, do you see that I've just included half of that inner loop? Well, you'll see tonight. Give it a good shot. You're going to have to use some cleverness. So good luck.
Mr. Shana,
Yes.
so